Hello everyone, it's December 20th, so let's do the 21st. So I finally set up my other laptop and I actually did a little bit of test this earlier today. The result was not good. I was expecting that using the MacBook Air, my other laptop, which was newer, and everything would become faster. But it turned out no, it was as slow as on this laptop. So it was no performance boost. I mean, all I can say is OBS is a very taxing software to run. But I think I will still change to the other laptop so that I can completely separate the work with my personal endeavors. I also watched a video today. I think first is number file, and then is 3 blue, 1 brown, and they're talking about. I mean, the number file video talking about the process, the definition of randomness, right? The random selection. It was very interesting. And later on in the 3 blue, 1 brown video, it was a discussion of 2 different methods to solve a problem, and it was mind blowing. It was good, like really good. I mean, like the number file videos with the first part and the second part, there are 2 parts adding together about half an hour, and then the 3 blue, 1 brown is 40 minutes video, but both are very captivating and just kept me glued into the screen. I mean, math is. I mean, some of the comments are quite interesting. So we all kind of. I actually also kind of think math is the ultimate answer to everything. But throughout the video, especially the number file video, you kind of see that math is just a tool. Like it's not any different from other tools we have, the physics, chemistry, whatever. It's just a subject, right? It doesn't hold the ultimate truth, and the answer coming from math changes depending on your definition, depending on how you define a problem. And how you define a problem is not something that math can answer for you, but we have to answer that ourselves. Right? We need to define it, and once we define it, then math can give you a definitive answer. But if we cannot define it, or we are just assuming, I mean, human perception experience is biased, right? And the way that we think, okay, I think this process is random, but actually it's not, because there are, I mean, talking about randomness, there are different types of randomness. I mean, in the video of number file, they're talking about different symmetries for randomness. You have rotational symmetry, you have transitive symmetry, right, regarding randomness. So like, how do you pick the randomness? What type of randomness are you picking? It's this is a question that math cannot answer for you. But once you decide, right, once you specify, okay, I want my randomness to be only rotationally symmetric, then the answer is definitive, like this one, right? And if you say, okay, I want my randomness to be transitive, then the answer is also definitive. But before we can arriving at these answers, we have to define it first. Yeah, so it's really good. Got me thinking. It's like Christmas gift from those channels. All right, so let's look at what you had today. We have an easy one called power of 2. It was an old question. 200 something. I've done this before. Wait, what the hell? Given an integer n, return true if it is a power of 2. Otherwise, return false. Okay, so without loops in recursion, I mean, one thing we can think about is just to turn it into a binary value, right? So we turn this into a binary value and count how many ones there are in it. It has to be 1, 1, and the 1 has to be in the front. So I can probably do this, right? Yeah, I mean, the first thing in my mind is never to do loops or recursion, right? The things that's in my mind is definitely binary number. And I'm pretty sure that that will be the actual solution that I have, binary number. Okay. Yeah, I can feel the speed. Actually, I didn't test this part in the new laptop, so all I test is open web pages. Open web pages is slow as what we have now, but maybe maybe it's faster to do. Maybe it's faster to type, possibly. All right, anyway, so we do the binary value, right? And then we just need to see. We need to. How can we write this in one line? I don't know. How can we write it in one line? I mean, what we can do. All right. How about this? Yeah, I kind of don't like this. I want to do this way. I want to know the number of bits. I can do that from here, right? So I can say len this -2 because we know let's start with 0b. So that is the total length of the binary, right? And then what we can do is just 1. We're going to left shift this thing, right? 1 left shift the total number of binaries. So that will be the mask, right? And then all we need to do is say we can do n exclusive or, no, not exclusive, n and this value, right? If the value, we're just going to return or return Boolean value, I think. And then we'll turn that into Boolean value, that's fine. So Boolean value. Okay, let's see. If it's 4, it's 1, 0, 0, right? So that will be 3. But 1 left shift 3. That's 8. So I actually has to be -3. Okay, so well, it's a 1, right? It's true. 2 is true. 3 is false, right? 2 to the 31 minus 1 is false, but let's say 2 to the 17 is true. Okay, n is power 2. Oops, daisy. 3 is false. Oh, of course. I think it's exclusive OR, man. Yeah, then it should be the reverse. So if it's equal to 0, that means it's true. There you go. Yeah, it's exclusive OR. Yeah, because the other one, when I say and, right? Yeah, and is not right. And is not right. Okay, let's try this. Oh, I didn't try the negative value. Shoot. Oh, it passed. And I didn't. I haven't done this before. Of course I haven't, because it's easy number, easy question. Oh, this is. Wait, hold on. How does the negative value work? Hold up. Negative value works as well? No, it doesn't work. N could be negative. and negative doesn't work. What should I say? Oh, well, I can, hold on. This is actually interesting. Negative value. It should not work, but in this case, it does. Oh, I was wrong. That's false. Okay, I got it right for the wrong reason. I got it right for the wrong reason. And it's a power of 2. If it's negative, it's definitely going to be false. And just because, oh my god, it was, but it doesn't matter. It doesn't matter because if it's a negative value, it's always not going to work. Look how lucky. I wasn't thinking about a negative value. I was not. 231. Well, use binary turn n into a binary value and exclusive OR with its mask. The mask is a power of 2 determined by the number of bits in n. Now I didn't consider negative values, but just out of pure luck, negative value bin of a negative values would yield a wrong number of binary digits for this solution. Thus, by mistake, we have solved the negative case as well. The correct way is to first check whether n is positive or negative, and then use the binary check. That's 01. Oh wait, hold on. How do we do the binary values? I forgot. I need to go to my Stack Overflow. I forgot. I think I answered that question and I forgot what I answered. Two's complement. Yeah, that's the one I wrote. Where's my answer? Using this and this, and a mask. 10 is 2's complement. I'll mask it and to the integer value. It's because this tilde is the tilde is the reverse of 2's complement. 2's complement is we reverse and plus 1. So tilde is -1 and the reverse. That's what the tilde means, minus and reverse. Therefore, mask is a number of bits, and then we do this, all right? And then we want the binary, and then the binary is, we want a binary, so binary representation. Usually we say reverse. So -6, we do this, and -1 in reverse. And then this one will reverse it, right? We'll reverse. And -1. Yeah, reverse -1. That's true. Reverse -1. All right, so we're using these two. I don't know if I can memorize this. But anyway, that's that. What's the time? 28. Got lucky on this one. 88%. Hey, this is not a recycled problem. Using n and oh, that is good. N and n-1. So if it is, then we say n-1 and what? And, right? If I AND these two, and the answer will be all ones. No, if it's AND shall be 0. And shall be 0. Yep. Ooh, this is good. Oh yeah, that's the trick. All right, the actual trick. I knew it. It gotta be an actual trick. I didn't think about it. All right, so this is the actual trick. All right, this is the actual trick. Reference. Return n larger than 0 and n n-1 is equal to 0. Which we can just say n not. All right, so we'll try solution 2. Yep. 1, 2. It'll be the same. I will submit this just for fun. It'll be the same. I don't think it will have any change in the time. Yeah, it's fine. All right, so I've done this. Let's roll another one. Validate UTF-8. Oof, this type of problem is always tough. Oh my goodness, how many hints can you give? Data. 1 to 4 bytes. So each byte is 8 bits. All right. So in total, it could be what? At most 32 bits. Hold on. Each byte is 2 bits, right? Why'd you count with 8? Yeah, each byte is 2 bits. So we can talk about 2 bits to 8 bit. Yeah, so that is 1 byte, 2 bytes, 3 bytes, 4 bytes. Hexadecimal, right? So each byte, so that contains 4 bits. 1, 2, 3. Wait, no, that's 2-bit, and that's also 2-bit. Wait, really? Okay, I'm confused. Now, 1 byte is 8-bit. Yes, that's 8-bit. This is 8 bits. That's 1 byte, 2 byte, 3 byte, 4 bytes. Right? Each byte contains 8 bits, and each hexadecimal is 4 bits. Yeah, that one is 4 bits. Because it's like f was 15, right? So it's 1. It's 1 1 1 1, right? That's 1 1 1 1. That's 15. That's 4 bits. Yeah. All right. Subject to the following rule: for a, let's say, 1 byte, so that's 8-bit. All right, if it's a 1 byte character, first bit. Wait, first is what? First is on the right side or the left side? The left side. That's the first bit. Okay, so that's a 1 byte. Yes, 8-bit. The 1 byte character. First bit is 0, followed by its Unicode. Followed by its Unicode. What do you mean followed by its Unicode? Hold on, do I need to, yeah, I need to get a bit bigger. Followed by its Unicode. Two, three, four, five, six, 7, 8. Oh, it's this, followed by whatever is inside this. Okay, so f is 1, 1, 1, 1. 7 is 0, 1, 1, 1, right? What if it's f and an f? Wait, hold on. Hold on, for a 1 byte character, the first bit is 0, followed by, for an n bytes character, the first n bits are all 1s. The n plus 1 bit is 0, followed by n minus 1 bytes, with the most significant 2 bits being 1, 0. So for this is n bytes. How many bytes? So this is 2 bytes. Right? So it's a 2 byte character. So the first n bits, the first 2 bits are all 1s. Oh, okay. So this is the actual hexadecimal. This is the actual thing. And then this is the UTF-8 encoding. So this does not translate to this. This is just the encoding. So the first n bits are 1s. The n plus 1 bit is 0, followed by n minus 1 bytes, followed by n minus 1. So there's a 2 byte. So 2 minus 1 is 1 byte. the most significant 2 bits being 1, 0. So we have 1, 1, 0, and the remaining will encode whatever this is. And if this, okay, I have 2 bytes, right? I have 2 bytes. So the first 2 bits are ones. Oh no, I have 3 bytes. Wait, hold on. Hold on. I have this one here. No, wait, this is 1 byte. That's 2 bytes. That's 2 bytes, right? So I have 2 bytes, and the first 2 bits are 1. 2 plus 1 bit is 0, followed by n minus 1 bytes, so the most significant in this. Okay, so this one, right? Isn't this also 2 bytes? This is 1 byte, and this is an oh, that's 3. Wait, hold on. I'm confused. I'm confused. That is 1 byte, right? This is 1 byte, and this is another byte. But I see this is 3, and this is 4. What? The least significant 8 bits of each integer is used to store data. This means each integer represents only 1 byte of data. Wait, I still don't understand. Do it again. Well, that's 1 byte, right? So this is a 1 byte character number range. All right, and the first bit is a 0. Okay, so if I have n bytes, so this one I say I have 2 bytes because that's 1 byte, and that's 1 byte. That's what I think, right? So I have 2. And this, we say we have 3 bytes. How'd you figure 3 bytes? Or, hold on. 1 byte is 8 bit, right? 1 byte is 8 bit. Then this is 1 byte, right? 1 hexadecimal. Each one is represented by 4 bits, so that's 1 byte. But isn't this one going to be, if we're talking about this, it'd be 1 byte and 2 bytes, and this is 3 bytes? It should be this. Huh? Hold on. How does UTF-8 work? I might need this actually. So UTF-8. I find that I don't understand. Do we have a easier way to go with UTF-8? How about this? I don't need to know the character list. I just want to know the rule. HTML UTF-8. Oh, this is not helping. Nah, this is not helping. This is just trying to tell you. Ah, I shouldn't have closed it. Here's the thing with DuckDuckGo. Like I click something, it doesn't open a new. Maybe I can change. Okay, so what are the rules in coding example? Okay. Number of significant bits in the numerical value of the coding point. First code point. Last code point. What's code point? Code points are 1 to 4 bytes, depending on the number of significant bits in the numerical value of the code point. Font table shows the structure of the encoding. The X characters are replaced. They didn't really say the rules. They just said a code point is this first code point and the last code point. So this one say have 1 byte, and this one says 2 bits, 2 bytes. Oh, that's what it says is the range. Oh, now I kind of understand. It's like this is the range. It's a number range. Oh, I know. Oh, it means from this to this. Jesus. Come on. Alright, now it makes more sense. So from this to this, so from 00 to, wait, 7 is 111. So 07 and FFFF. So we leave the first as a 0. Alright? And then the next value is going to be plus 1 is 8. 0. 8 0. So from 8 0 to 8 0 to 07. Wait, 8 0 to 07. That's 3 bits, right? No, hold on. A 1 byte character. Wait, still. Now, what is 1 byte? What is a byte? A byte is it is 8 bits, right? It is 8 bits. Oh, I think the byte is referring to this. That is a 1 byte character. That is a 2 byte character. That's a 3 byte and a 4 bytes character. And this 1 byte character has 7 bits to store the value, which this is 7 bits. Now a 2 byte character can store well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We can store 11 bits, right? So we can store 11 bits from 80, right, to 7FF. So 7FF is 111, and we have 11111111. That's 11. Ah, now I see. Now I see. So the bytes is referring to this column. I thought the bytes referring to this column. Okay. Okay, so yeah, that's the range. From this range, and then from this range, that's 3 bytes, and from this range, we have 4 bytes. Right, 4 bytes. We have so many we can take into consideration, and then we need. But that's why it's not 7 again. That's because actually I don't know why it's not 7 again. Now we go 1 0 1 0. Our ending is 1 0 1 0. That is very interesting to say the least. I mean, it will be this one plus 1, right? So that's 1 0. Hold on, 7FF, right? So it's like this. 7FF plus 1, so 0 0 0 0 0 0. So it should be 1 0 0 0, right? That's 1 0 0 0 0 0 0. That's not 8. 8. Wait. Hold on. 7F plus 1. 7F plus 1. How would that become 8 a 0? Zero is just 0 0 0 0. 8 is 1 0 0 1 0 0. That's 8. Oh, okay. Okay, that's fine. That's fine. Oh my God, I wasn't thinking. So I plus 1. So that shall be 0 0 0 0, which is 0 0. Shouldn't that be A 0 0? Yes, that's A 0 0. Okay, this one still makes sense. Okay, still makes sense. So from this transition, so this one basically is going to be 1 0. Oh, that makes sense. 1 0 0 0. Okay, so 1 0 0 all the way to 1 0, all the F. I was expecting to have a 7 here. But it is 1 0. We'll have a note. Yeah, it should be this, right? The current limits coding through, so it's actually smaller to match the limits of UTF-16. All right, okay. So we got that out of the way. So finally I understood. So the input is an array. So whether it's a valid encoding, okay? So the input is an array of integers. Only the least significant 8 bits of each integer is used to store the data. This means each integer represents only 1 byte. 8 bits. 1, 2, 3, 4, 5. Oh, wait, 1, 2, 3, 4, 5, 6, 7, 8. Least significant 8 bits. Wait, so. Huh? Oh, so you're telling me, so that is the encoding. So you're telling me the least significant 8 bits. Wait. So the least significant 8 bits, which is this thing, right? That's not the least significant 8 bits. That's just the last value. So you're telling me this represents the data. So each integer represents only 1 byte of data. So this one is a 3 byte, right? We have 3 byte. And we turn into octet sequence. We have this, this, and this. And it is a valid of a 2 bytes character followed by a 1 byte character. Oh, so each value okay, hold on. Input is an array of integers. Only the least significant 8 bits of each integer is used to store the data. I mean, your integer is only 255. Oh, 255. Wait, what's 255? That's 16. It can grow to 16 in length, right? Wait, what's 235? Oh, I think they already do it. Hold on. Oh, it's gonna take forever. So I think 197. This. Yeah, that's not 197. That's 8, right? So 1, 2, 3, 4, 5, 6, 7. 2 to the 7th. I don't know. Binary 197. Right? It's 11000101. It's 8-bit. Yeah, 225 is 8-bit. Yeah, that's 8-bit. Every value only has 8 bits, so this information is not really necessary. So all we need to know is each value represents a byte, all right? So we just need to know whether it's valid. So that means if okay, I want some hypothesis. So my hypothesis is what the question asking for is, and it has to be sequential. So if I swap these two, right, then this one will return false, because right after this value, right after 197, I shall expect a 1, 0. But now I don't give a 1, 0, and it's a false. Okay, so now we have this. So we have a 1, 1, 1, 0, right? So we have a 1, 1, 1, 0. That means that's a 3 byte. The first 3 bits are all ones, and the fourth bit is 0, means it's a 3 byte character. The next byte is a continuation byte. Starts 1, 0, that's correct. But the second continuation byte does not start 1, so it is invalid. Okay, so how about if we write it like this? 1, this, and that is correct. I think that is true. Okay. What if a value that does not have this, I don't know, 123? Yeah, let's try 123, right? 123, 1, 2, 3, 4, 5, 6, 7, 8. Can we get 255? Right, let's get 255. Let's get, I don't know, 255 and 140. 140 and 140. That should be false because this one doesn't have this format. It's false. Yep, it's false. Okay. Okay, so basically, we're gonna read from left to right. We check the first value. If the first value, we have 4 different scenarios, right? Okay, so we can create a mask, and we just check 4 times. And if it's this, then we're good. We move on. If it's this, okay, then we require the next one to be this. It's deterministic, right? It's deterministic. Because it said it's a 2 byte, so we check the next byte. If it's good, then we go to the next one and we'll So if not, okay. Wow, it's just like took so long for me to understand. Is that why people don't like this question? I do find it hard to understand. 393. Well, I hope my understanding is correct. And this one is like, man, I don't think it's really interesting. It just took you a while to understand. I mean, it's good. I never really understand the UTF, but now I see how it goes. Yeah, it makes sense. It makes sense because when you transfer data, right, it's a stream, and you get value one by one, right? You get value one by one. And when you get value one by one, how do you know where is the cutoff, right? You don't know where the cutoff is, but now you know because the cutoff is given to you in the first byte. So it does make sense. Okie dokie. So what we're going to do? What we're going to do, we're going to say I is equal to 0, right? And while I is smaller than len data. So each data comes out. So we have a mask, right? We have a mask. So we say, yo, mask. If I how do we check for mask? Exclusive OR, right? So it's not I, the data I. Exclusive OR. So the first mask is going to be 0. Oh, shoot. No, I need to pick out the first 4. Alright, hold on. So I need to pick out the first 4. So how do we pick out? So it's gonna be and, right? And I'll pick out. So that's a 1 left shift. 1 left shift 7. 1, 2, 3, 4, 5, 6, 7. Yeah, left shift 7. So if this left shift 7 and, right, so that left shift 7, we end. Oh, we can directly check. If left shift 7, so it's 1, 0, 0, 0, 0, 0. And if I ended it, and the result is 0, then it's fine. So if not, right, if not this, then continue. Right, because this is a 1 byte situation. All right, Aleph. So now data I, we're gonna and that's the first mask. What I say, second mask. All right, we actually like to say M1 is equal to 1 left shift 7. All right, so this corresponding to 0, 1, 2, 3, 4, 5, 6, 7. Right? Mask 2. Oh shoot! With mask 2, we have a bunch of other masks. Oh, but these masks are the same. Okay, mask 2 is equal to the first 3, so it's going to be, oh shoot, 1 left shift 7 or 1 left shift I should say plus 6 and plus 1 left shift 5, right? Because we have 3. 1, 2, 3, 4, 5. Yeah, so that is 1, 1, 0, 1, 2, 3, 4. So mask 3 is equal to, oh, why can't you say mask 1? That's mask 2 plus 1 left shift 4. Right? Yeah. So this is 1, 1, 1, 0, ba, ba, ba. 3 left. And mask 4 is going to be mask 3 plus 1 left shift 3. It's 1, 1, 1, 1, 0, ba, ba. 1, 1, 1. Oh, shoot. That has one more. 3. Okay. So, and we have a mask underscore is equal to, oh, now I see. So mask 1, mask underscore is 1 left shift 7. So M1, right, plus M plus 1 left shift 2. So this is 1, 0, 1, 2, 1, 2, 3, 4. Right, so that's that. And M2 is going to equal to this. Wait, what are you doing? That's not shift 6. Right? Oh. Mask 1. Let's call it mask 0. Mask 0, mask 1, mask 2, mask 3, and mask 4. Right? So this is going to do mask 0. Right? And this is going to do max 2. Right? We'll try to find this. Right? If it's find this, so that will get the first 3, and we'll say if this, that's just a mask, and we have to also equal to, if this is equal to int 1, 1, 0, 0, 0, 0, 0, 0, right? So that's this. If this is equal to this, then we need to check 1 value next. Can we like I'm trying to make it as automated as possible. Okay, this is fine, but can we make this into some sort of, I don't know, that's just the masks, right? Is there just a mask? You know, we grab it, and then we do this, and I shall be able to know how many there are, right? So it will be better if I put this whole thing. Let's just say masks equal to 1 left shift 7, 0, 0, 0. 0, 0, 0, 0, 4 zeros. And then comment here, I'm going to say mask 0 is equal to this. And then, instead of say 1, masks 1 equal to masks 0 plus this. All right. So there can be masks 2, 0, 1, 2, 3, 4 equals. Okay, so that's we handle all the masks. Now in here, once we handle all the masks, now we can say else. Actually, don't say else because it continue. Now just say for j, right, in range 2 to 4, actually 2 to 5. So we're gonna handle these 3 situations. If data I and that is going to be masks 0. There's going to be masks j, right, equals to integer something 2, right? If it's equal to this, and then we going to say blah blah blah, and else what? Else, which means that we don't break out. So this one eventually wouldn't break, right? Else, which means we didn't break, which means none of this match. So that's just going to return false. All right, so now we equal. Now we find out that it is. So then, based on I, now we know how many we have. Oh, I have 2, I have 3, I have 4, right? So we need to check so we find a j, right? Then we just say for this in range j minus 1, right? That's the number I need to check. So we're going to go I plus equal 1 first. So we move once, right? Move once. Then we say if data I and masks 1, right, equal to int something 2, and then we'll continue. But if not equal, then we're going to return false. All right, okay. So this one will go through if all 3 is good, right? So it never return false. If all 3 is good, then we don't do anything, right? If all 3 is good, then we don't do anything. And I plus 1, so we check the first one. Coming up, I plus 1, we check the second one. And if both are equal, then the current is good, right? The current is good. And we check all 3 and it's good, then we don't have to keep going, right? Because it's only once. So we're just gonna break this. Yeah, that is a break. Because if this is good, then we check. Either we return false or we're good. So we break it, right? Break this. And then else return. So once we're all done, I plus equal 1. Move on to the next one. Which means I should not say continue. It shall be if this, right? if this not one by situation. If it is a one by situation, we're fine. We don't do anything, right? If it's not a one by situation, if it is a one by situation, we immediately go ahead. If it's not one by situation, we check these three situations, right? And one of them will match. And if they match, we check the remaining, see if they match. If they match, then we break out, don't do this, plus equal to 1, we keep going. And then, blah, 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 everything is done when the return true. All right, so last piece is going to be handling this, right? So this is depending on J, right? We're depending on J. So J determines how many ones we have, right? So it's going to be J times 1, right? J is how many ones we have. And this one plus 0, right? How many times 0? It will be 8 minus J times 0, right? So if J is 2, then 7 minus 2 is 5. I'll have 5 zeros. 1, 2, 3, 4, 5. Hold on. 1, 2, 3, 4, 5, 6, 7, 8. 8 minus, 6, 6. 8 minus 2 is 6. My God. Right? So we do this. And then this is deterministic. It has to be this way. So this one I can just go right, say 1, 1, 0. No, I put it 1. Oh, did you realize something? I did. I did realize something. Because this mask is getting, the mask is getting these, right? But then the actual thing we want to match is actually mask 0. It's 1, 0, blah, blah, blah. So we just do that. If not equal, then return false. Otherwise, keep going, okay? So that is my solution. All right, let's try. So I have this will return true. Second one is this shall return false. Data, valid, data. See, mask is not defined. Of course it's not, because it's not called mask. It's called masks. Where? Here. Okay, these pass. All right, I'm a little bit worried, so I'm just gonna make it more explicit. Yeah, here as well. Like just in case. All right, I mean, equal shall have. You know, I think it's fine. Equal shall have the last priority, the lowest priority. All right, I don't have any other examples to use, but I'm pretty confident. All right, how about these? These are new situations. Yep, they're good. All right, let's try it. Runtime error. Oh, whew, shoot, that's true. Uh-oh. That is a good test case. Ah, shoot. I should have seen this. That should be false. Yeah, so what happens is I don't have enough to go for. right? So I plus equal 1, and we say if I is equal to len data, right? And for this case, I am just going to say n is len data. So we're going to go n. And if any time this becomes n, or not data, return false. Yep, that's my mistake. Okay. So anytime I handle this, okay, so I'll try it again. All right. I don't know why they have so many hints. I mean, this is not a difficult, not a difficult problem, but it did take me a long time to understand how UTF-8 works. I mean, the problem description definitely can use some improvement. I mean, the solution is very straightforward. The solution is straightforward, right? Straightforward. We check the input values one by one. All right, we check input values one by one, and match it to the 4 scenarios. And if it's the 1 byte scenario, it passes automatically. Right? If it's any of the other 3 scenarios, we continue. Right? We continue checking the remaining values. Checking the remaining values. Checking remaining values. At any point, I check fails, we return false. And the check is conducted via bit manipulation. I mean, I'll call it ON, right, where n equals len data. I will run it 100 milliseconds, and we got a 95. Yeah. All right. I think this one has a solution, so we can take a look and see how people complain. That's not a valid one. This is one will return false immediately. All right. It's a 5 byte. Wait, hold on. We can do 5 bytes? Yeah, I can only have 1 to 4 bytes long. Like, what the hell? String manipulation. Oh yeah, that Made me think. Maybe that one is easier. All right, we just check against the string. Yeah, it could be. And then we can compute the number of bytes. And yeah, we count number of bytes. Yeah. Yeah, bit manipulation. Yeah, I put them in here, so it's the same thing. Mask 1, mask 2. So I think they uses this. Let's start with here, and number of bits 0. We just add number of bits. We move masks. And then comma out. Now we know the number of bytes. If it's 0, it's this. If it's 1, or then if number of bytes is not, then we check. I see. That's actually a good solution. That's actually I think I'll actually try to write it. It's a good solution. All right, so I don't know why people don't like this question. I think it's all right. And the official solutions bit manipulation, I think it's better. I mean, I use a different way. Both are good. I think both are good. But this is the official solutions bit manipulation. What do people say? So that is the same feeling. Yeah, I would say it's a stupid question. All right, so what does that one say? So that one says we can only have 2 masks. So we have M1 and M2. And M1 is 1. Actually, it will be easier to do. M1 is 1 left shift 7. M2 is M1 plus 1 left shift 6. So we only need these 2, right? And then all the others can be derived. Right? So we say for num in data, right? So once we hear every time the number of bytes, number of bytes is 0, right? So if number of bytes is 0, then we need to check how many number of bytes there are. So we need to, starting from the mask, from M1, right? We start from M1, so we can say mask equals M1, and we say while num and mask, right? So M1 is the first one. While M, this number of bytes plus equal 1, and mask equals mask right shift 1. Right shift, we move the 1 to, okay, that's smart. No, this is smart. This is smart. To, how should I say, this is smart. We to check the next by a bit, and then come back up. So we check the next bit, the one, blah, 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 when we're all done, right? So this one all done. When all done, we check. We're going to say if number of bytes is equal to 1, or number of bytes is larger than 4, then return false, because that is no good. All right. Otherwise, we go back up. So else. So now we have a number of bytes. So then we just every single value with that number of bytes, we need to check if it fits M2, right? So in that case, we can say if num and M2 is equal to this, equal to M1. Alright, which means that if it's not equal to. Did you just say not? Come on, man. I was about to do the same thing. So if it's not equal to M1, then I'm going to return false. Right? Which I think I can just do it here. If it's this, then return false. If it's true, oh, it's not equal to. Else, when it's equal to, then number of bytes minus equal to 1. Then at the end, return true. Okay, let's try. Ew, that was not right. Okay, it's fine. It's fine. It's fine. What I can do, I can print number of bytes. 2 bytes, right? That's fine. 2 bytes is fine. Okay, so now the next number and M2, if it's not equal to this, then we'll return false. Where do we return false? Num and M2. That's 0. What? I need this. M2 is 1 left shift 7. Oh my god. Oh my god. That should be right. That's still not right. What? This is correct. Number. Hold on. Number of bytes minus equal 1, minus equal 1. So this one says 2 bytes, right? And, oh, hold on. So if there's a, otherwise, I think, yeah, we have the remaining bytes in that minus equal 1. There we go, there we go, there we go. Yeah, we have to minus equal 1 there as well. because 2 bytes is including the current one is 2 bytes. So after the current one, the remaining one actually needs to minus equal 1. So with this, okay, so the last one failed. So this 237. What's 237? Binary num. So that's 3, right? So it was 0, mask is this, blah, blah, blah. So we can actually check. Oh, number of bytes. So return number of bytes is equal to 0 when we come out. There we go. Oh. Oh, hold on. If number bytes is larger than 0, then we do this. If this or this return false, I can say elif. Then we do this. Yep. I think it's exactly the same as the solution. We can actually check the solution again. Let's kind of double check what was the... Was it that complicated? I don't remember it was that complicated.